In this video, I'm going to be talking about electronic light spectra. So I'm going to discuss something known as the electromagnetic spectrum, and I'm also going to talk about individual atomic spectra. So first, the electromagnetic spectrum. So this is a spectrum that shows where all different types of light radiation fall in terms of energy and wavelength. So we can have one end down here, one end down here. So this end is going to be low wavelength. And of course, if you remember in the last video, I said that wavelength and frequency were inversely related. So if the lowest wavelength light is over here, this also has to be the highest energy. And also the highest frequency, because remember, energy and frequency are directly related. So over here will be the highest wavelength and the lowest frequency and energy. So the highest energy or highest frequency radiation are gamma rays. Now, so gamma rays are and that's why gamma radiation is so dangerous. They're insanely high energy light, and they can be very, very damaging because of how high energy they are. And as a result, they're extremely low wavelength. The next highest energy, and also again highest frequency, are X-rays. After X-rays is the UV region. So UV stands for ultraviolet. So I'm going to put it down here. After UV is visible light. So this region right here is the only light. So again, all of these are different types of light. But this region right here is the only region that we can actually that humans can see with the naked eye. Different types of animals can see various types of light, and it's actually kind of cool. You can try Googling the types of light that other animals can see, and it's really cool to see what the other animals actually see. Because some can see UV radiation, some can see IR, which is the next one, and I don't know, at least I think it's kind of cool. So after visible light, as I just mentioned, is IR, which stands for infrared. Infrared. And then after IR, the highest wavelength and thus lowest energy are radio waves. And those are the actual waves that radio stations use to broadcast. Now, within the visible light, this end of the visible light spectrum, right here, so which is the highest energy end, is blue light, and this end over here is red light. Red. So blue light, out of all visible light, blue light is the lowest wavelength, but highest frequency and highest energy. Red light is the highest wavelength, but the lowest frequency and lowest energy. So now I'm going to talk about something called atomic spectra. So when atoms are excited, and what excitation means is basically they're hit with light. So atoms are hit with light. So you shine light of a certain type of wavelength, and the wavelength varies, but usually some light in the UV range. You shine that on various atoms, and they'll get excited. And in what exciting means, it will make more sense, hopefully, with some of the next videos later on in this chapter. But basically, it means that it moves an electron to an excited state. So, basically, in the basic structure of an atom, we have a nucleus, and then we have a bunch of orbitals with electrons circling the nucleus. And you can say an electron will go from the orbital it starts in and it'll jump up into a higher orbital. That's what it means to get excited. Right? That's called an excited state. But atoms don't like being in an excited state. So after that happens, they want to go back down to the original state, which is known as the ground state. That's the lowest energy state, and that's what they're most comfortable in. And that relaxation, so when it relaxes back down to its ground state, that's when you see light given off. Because, if you recall, all energy in the universe has to remain constant. No energy can ever be gained or lost. That was the first law of thermodynamics that I talked about in a previous video. So, if this electron is moving back down to a lower energy state, which, again, the ground state is the lowest energy state, that electron has to lose energy. And it can't just vanish into thin air, so it's given off in the form of light. So light that you see being given off by things is basically by electrons relaxing back down to their ground state. So every type of element has a unique atomic spectra. So an atomic spectra is basically a pattern of light. So let's say we have, and I'm just kind of making this up. So for one, we might have something like this, some blue lights, blue here. Then it might go to pink like this. Green, and I'll say to orange. Right, so that might be in a spectrum for, and so this would be an atomic structure for one element. When another element could have say something like this. Let's say it has no green, because it doesn't have to have every shade, and something like that. See, so basically every element has it. Oh, I'm sorry, that was not on the screen. There you go. So this could be two representative atomic spectra for two different elements, and every single element has its own unique atomic spectrum. So if you are trying to identify the elements that are present in a sample, you could bombard them with light and measure their atomic spectrum, because various atomic spectra are already known, so you can compare it to known atomic spectra, and it's a way to determine what types of elements are present in a sample. Now, one last thing I do want to talk about in this video still is there's a way to calculate the amount of energy that an electron will give off, depending on how much it drops in energy when relaxing back down to its ground state. And it uses something called the Rydberg equation. So the Rydberg equation says that the energy equals, so a constant, which is the Rydberg constant, so it's negative 2.18 times 10 to the negative 18th joules. So again, this is the Rydberg constant. And you multiply that by 1 over nf squared minus 1 over ni squared. So what these n's mean is, so again, this is something that will make more sense based on one of my next video, but n is the principal quantum number. So the principal quantum number just tells you basically what number orbital that electron is in. So the basically the final orbital. So again, this can be used to calculate the amount of energy absorbed when going to an excited state, or the amount of energy released when going back down to a ground state. So this F just stands for final. So the final orbital that it ended up in and the I is initial, so it's the initial orbital that started it. Now, and these are just numbers, like whole number integers. So, for instance, this first layer would just be 1, so its n value would be 1. This would be 2, 3. If there were more, it would keep going, 4, 5. So these are all just going to be whole number integers based on what level orbital it started and ended in. And so that will actually give you the total energy either absorbed or released by an electron when moving between different orbitals.